let's wrap our heads around something pretty wild. Imagine the coldest anything can possibly get, absolute zero. You'd expect everything would just be frozen solid, completely still. But what if I told you that even then, at the absolute limit of cold, things are still moving, still wiggling? It sounds completely bonkers, but it's one of the weird, fundamental truths of our quantum universe. And this quote, man, it just nails it. This isn't just some nice poetry, it's physics. It's telling us that the universe never, ever truly goes silent. Even in that deepest quiet, there's a fundamental pulse, a motion that you just can't get rid of. And for the very first time, scientists have actually taken a picture of it. So yeah, that's the million-dollar question, isn't it? How in the world do you photograph a single molecule when it's as still as it can possibly get? I mean, it's like trying to take a picture of a whisper. To pull it off, it took a technique that was incredibly clever and, well, literally explosive. Okay, so before we get to the wild camera they used, we need to understand exactly what we're trying to see. This constant hum, this baseline motion of reality, it has a name. It's called zero-point motion. Here's the thing you've got to get: the basic rules of quantum mechanics actually forbid perfect stillness. It's because of the uncertainty principle. You can't know a particle's exact position and its exact momentum, how fast it's moving, at the same time. If it were perfectly still, its momentum would be zero, and you'd know its position perfectly. Nature says, nope, can't do that. So there's always a little bit of energy left over, a little bit of jiggle that can never be erased. It's literally woven into the fabric of reality. This is a great way to picture the difference. In our big, everyday world, if you roll a ball into a bowl, it eventually settles down and comes to a complete stop right at the bottom. But in the quantum world, that ball is more like a fuzzy cloud of probability. It never settles into one single spot. Instead, it's always sort of fluctuating around that lowest point. It never, ever truly stops moving. Okay, so we know this quantum jiggle has to exist, at least in theory. But how do you go from theory to actually seeing it? Well, to do that, scientists built something you could call a molecular blast cam. And yeah, it's as cool as it sounds. So the team zeroed in on this one specific molecule, 2-iodopyridine. It has 11 atoms, so it's complex enough to have some interesting wiggles, but it's also small enough that they could actually analyze what was going on. The plan was simple, in concept at least. Isolate one of these molecules, chill it way down to its quietest state, and then snap its picture. And the process they came up with is this incredible, kind of violent three-step dance. First, you target one molecule. Got it? Second, you blast it with an insanely fast pulse of X-rays. And third, you just sit back and read the pattern of the debris as the molecule, well, as it blows itself apart. The name for this technique is Coulomb explosion imaging, and it's pure genius. That X-ray pulse is so incredibly fast, it acts like the ultimate camera flash. It rips all the electrons away from the molecule before the atoms even know what's happening. And once those negatively charged electrons are gone, you're left with all these positively charged nuclei that absolutely hate each other. They violently fly apart in an explosion. And by tracking exactly where all those pieces fly, you can perfectly reconstruct the shape and position of every atom the instant before the blast. You literally freeze that tiny quantum jiggle in time. So they did it. They took the picture, they mapped out the shrapnel from the explosion. What did that pattern actually show them? What did this invisible jiggle finally look like? And this is the absolute key. If the motion was just leftover heat, just random thermal jitters, the fragments would fly off in a simple, random way. But that's not what they saw at all. The data, the pattern of the explosion, only made sense when they included these fundamental quantum fluctuations in their models. And here's the kicker. It wasn't just random shaking. It was a complex, correlated pattern, which means the atoms were moving together. So what's the bottom line? What did this groundbreaking photo actually prove? Well, it boils down to three huge things. One, zero-point motion isn't just some mathematical idea. It's real and we can see it. Two, it's not just one atom shaking by itself. It's a collective dance, a synchronized wiggle across the entire molecule. And three, the specific pattern of that dance shows us the molecule's favorite ways of breathing, even when it's in its quietest possible state. Now, you might be wondering how physicists actually talk about this. There are a couple of different theoretical models, and they use slightly different language to describe how this is all happening. But, and this is what's so important, it doesn't matter which one you use. They both predict the exact same results, They are in total agreement about what this experiment shows us. So, realizing that this motion is a real observable thing is a massive step forward. But, it also brings up some pretty big questions, and honestly, a few popular myths, so let's just clear the air on a couple of things. First up, the big one. If you've sucked out all the heat, all the energy you possibly can, where is this motion coming from? Is it some kind of magic energy from empty space? And the answer is a hard no. It's not motion from nothing, it's motion from rules. It's a direct result of the fundamental constraints of the universe, like the uncertainty principle we talked about. You simply aren't allowed to be perfectly still. That inherent fuzziness is the motion. And that leads us to the biggest myth of them all. If there's always this constant motion, can we tap into it? Can we build a free energy machine that runs forever on this zero-point energy? Yes, sorry to burst that bubble, but that's a no-go. Think about that ball in the valley again. It might be jiggling a little, but it's at the absolute lowest point it can be. To get any useful work done, you need energy to flow from a high state to a low state. You can't get any work out of the absolute bottom of the barrel. But what's so powerful about this whole thing is that it's not just a one-off picture. It gives us predictions we can actually go out and test. For example, the theory says if you swap out the light hydrogen atoms in the molecule for deuterium, which is basically a heavier version of hydrogen, that the jiggles should get smaller. And that's exactly what they can see. The heavier molecule has a noticeably smaller jiggle. And that's why this is so exciting. This is just the beginning, not the end. It opens up a whole new playbook for scientists. Now they can start swapping out all sorts of different atoms. They can gently warm up the molecule to watch the dance change, use lasers to line it up perfectly before they blast it. They can even try to take a movie of the breathing over time. So when you boil it all down, why does this matter? Well, this quote right here says it all. For decades, we've been really good at studying molecules when we blast them with energy and make them loud and excited. But now, for the first time ever, we have a camera that can image the fundamental, organized, coherent nature of matter when it's in its quietest possible state. We can finally see the whisper. And that really leaves us with one final incredible thought. We've built this amazing blast cam to see the quietest jiggle of a molecule. And it just makes you wonder, what other secret, fundamental whispers of the universe are out there, just waiting for us to invent the right kind of camera to finally see them?